All right, so now what we're going to be looking at is we're going to be talking about double integrals over a general region. So sometimes what we want to do is we want to find the volume of a surface, but it's not necessarily over like a rectangular region. The process is going to look somewhat similar. I mean, there's some key differences, and we'll talk about some of the key differences. And what we'll start out talking about is we're going to start out talking about like a disk or a region, or the region over which we're actually going to be taking that double integral, over which we're going to actually find the volume for that region. So we're going to first we got a function, okay? We got f of xy, all right? And f of xy is some function, and it is going to be defined and integrable. That is that we can take an integral of it over our chosen region, okay? So that is that we actually can do that, all right? And what we're going to do is we're going to think about taking that double integral for f of xy, and we're going to imagine that we're on the xy plane. Okay, so we got this, we're on this xy plane, and I'm going to actually draw a rectangle. And so I've got a rectangular region. We know how to actually take the integral over that rectangular region, right? What we're going to do then is we're going to say, okay, let's imagine that I got this region here, and this is what we're going to call my region D. Okay, so D is a piecewise smooth region, all right? And when we say smooth, that means that there's no holes in it, doesn't have any like weird stuff going on. And in fact, it's also piecewise smooth closed region. So we've got this closed region. What we're not doing is we're not getting like something where it just, kind of extends out into infinity, right? It's like we could actually define the entirety of the region that we're going to be taking our integral on. Now, what we're gonna do, and this is somewhat theoretical, but our tools are gonna kind of help us do this kind of thing, is we're gonna imagine that we have another function, and it's g of xy, and it is a piecewise function, okay? And it'll be g of xy is gonna be f of xy, right? If xy is in D, is inside of this region, right? If it's in this region right here. And it'll be 0 if xy is not in D. But it is in R, but not in D. So what that's going to allow us to do is it's basically going to it'll zero out anything that's not within the region, okay? So this is like out here, we're going to have the value of, or let's, what should we do? We'll make little dots. Okay, there we go. Okay, in this outside region here, what we're going to do is we're going to say, you know what? If our function, or if we are not integrating over a region that's in D, we're just going to zero everything out. We're not going to actually take its value, and we're going to actually make it 0. So that way, that's going to restrict our function only to the region D and allow us to think about everything in terms of taking the integral over the rectangular region, right? So if you just think about it, right, that's just saying, oh, well, because, well, like the function's equal to 0, right? We're just flat onto the region. I don't know how else to say it. So that's going to be kind of like the basic theoretical idea that we're going to be working with here, all right? Let's give some machinery to this idea of D. What is D exactly? And D is going to be kind of like a handy thing for us to work with as well. Okay, so now let's talk about this region D. And we're going to use this function g that we're talking about, but notice that g is a function of just a single variable. And if we have h here too, notice that h is just a function of a single variable as well. We're going to define our region D as being of type 1 if it lies between two vertical lines and the graphs of the two continuous functions g1 of x and g2 of x. All right, so what we want to imagine here is, let's just imagine that I've got, again, we're going to be looking in the xy plane because that's how we're going to define our domain. That's the region that we're going to integrate over. And so we might imagine here's g1, g2 of x, here's g1 of x, okay? And then here are our vertical lines. This would end up being x equals a and x equals b. So if we kind of want to think about this, this is going to end up being y1, this will end up being y2. And so we're going to actually integrate over this region right in here. And where this is going to end up becoming really important and very valuable for us is that when we set up our double integral, it's going to be the double integral, okay? And then this is going to be, we're going to integrate from g1 of x to g2 of x. And then we'll go from x equals a to x equals b. And so this will be then f of xy, whatever that function is. And then this will be dy dx, right? Remember that g2 of x is going to be a function of y, g1 of x is going to be a function of x, right? And then x equals a and x equals b, those are going to be bounds for our x values, okay? So if I kind of think ahead a little bit, what's going to happen here is that I'm going to integrate with respect to y, just like I did over the rectangular region, and then I plug in functions of x. So what that does is that's going to get rid of all of my y's. Everywhere I have a y, I'm going to plug in these functions of x, all right? Work them just like as if I was working a definite integral, okay? Then I'm going to integrate with respect to x and go over the bounds from a to b. And that's called D1, right? Or excuse me, that's called a type 1 disk. Type 1 disk is our functions are with respect to x, right? And our bounds are with respect to x, all right? So key point. Let's take a look at a type 2. A type 2 now, again, we're going to be in the xy plane, okay? So here's type 2. Again, we're going to be in the xy plane. And what we're going to do now, though, is that we'll have a function of y, right? Call this h1 of y. And then we'll have another function of y, say it looks like something like this, okay, that's h2 of y. And then we'll have y equals a and y equals b, okay? So in this case, right, we're going to integrate with respect to x first, okay, because these are going to be x equals h1 of y and x, or x1 equals h1 of y and x2 equals h2 of y. And then we'll integrate from a to b, but in terms of y. So when we set up our integral, what it's going to look like is it's going to be, we're going to go again from a to b, okay? But now we're going to have h1 of y, h2 of y, okay? We'll still have f of xy, that's our function, okay? And then this will be then dx dy. So we'll do our x's first, because these are actually x's, right? It's x1 equals h1 of y, x2 equals h2 of y. Those are actual x's, okay? And then we'll integrate from a to b. And this is our region. So when we think about why it is that we're actually going to do that, so our why do this? The reason for us to do this is because sometimes it's easier to integrate with respect to y. Sometimes that's just the easier thing to do. Or x. It just depends. It depends. And hard and fast rules, not really. I mean, really, sometimes we want to look at the graph or we want to look at the region that we're graphing over, okay? But basically, we're given these two different choices, right? On the one hand, we're given the idea we can use a type 1, where we've got our y's in terms of a function of x, right? And then our bounds are on the x-axis. Or we have a type 2 in which what we have is we have our functions in terms of y and our bounds are on the y-axis, okay? So there we go. That kind of sets us up these type 1, type 2 regions. So let's take a look at doing this. Let's take a look at a single region and let's turn it into either type 1 or type 2. You can do both. And that's pretty much true in any case. Sometimes you're not going to be well served to turn something into a type 1 or a type 2 region. You're just going to have to kind of like figure that out as you do kind of work with it. But what we'll do here is we'll say, okay, well, I have these two curves, y equals square root of x and y equals x cubed. And those two, you'll notice that we've got basically, if we want to say g1 of x, the bottom curve, is going to equal x cubed, and g2 of x will equal the square root of x. And this is if we were going to write it as type 1. Type 1, remember that our functions are functions of x, okay? And then our bounds will be in terms of x as well. So we're going to go from 0 to 1, okay? And so a will equal 0, b will equal 1. By the way, you can figure that out just like you did inside of your second semester calculus course by finding the intersection of those two curves, right? Setting square root of x equal to x cubed, okay? So basically that would give me that x equals x to the 6th when we square both sides. And so x must equal 0, okay? And then we could actually also divide through by x, and that would give me that x to the 5th equals 1. So x has to equal 1. So x equals 0, x equals 1, and that gives me my bounds. Just kind of like a little review of how you could go about doing that and finding your bounds. All right, so that's a type 1. Now what about a type 2? So a type 2 now, what we're going to do, we've got to switch it and make it in terms of a function of x, functional y now. So y equals root x, what we'll do is we'll square both sides, and we get x equals y squared. And then, in addition to that, we'll take y equals x cubed, we'll cube root both sides, and we get x equals the cube root of y. Okay? Now what I need to do, my y2 and my y1, my y1 is going to be the one that's closest to the y-axis. Okay? So that's this line y equals the square root of x. So notice that the position, right, the relative position of the two functions, right, like g1 of x before was x cubed and g2 of x was square root of x. We're now going to have that h1 of x, or h1 of y, is going to equal y squared. And h2 of y equals the cube root of y. Okay? Because the cube root one, right, okay, this one here being x equals the cube root of y, is actually further away from the y-axis. Okay? When we talk about top and bottom, but we switch our orientation, remember we're going to be talking about left and right now. Okay? So make sure that you're actually careful with that. You're probably going to have to draw some graphs in order to make that determination. Otherwise, it's going to get a little frustrating. Okay? Now, the second thing that we've got to do is we've got to actually find our bounds. And if I go in here, here now is we're going to be looking in terms of y. So the y value, or pardon me, on the y-axis, this is y equals 0. That's going to be the bottom end. And then right here, and I know I did not do it justice, but y equals 1 is going to be the top end of that interval as well, because that point right there happens to be, in fact, 1, 1. Okay? So our a is going to equal 0, and our b is going to equal 1, so that'll give me the bounds of my bounds of integration. So a couple things to just remember as we're kind of turning something into a type 1 or a type 2 region. One is when we talk about which one's g1 of x and g2 of x, the one that's furthest away from the axis that you're working with, in this case the x-axis, okay, is your g2, the one that's closer is your g1. Top minus bottom, okay, or top over bottom. But when we actually start thinking about it in terms of a type 2, we want to get, it's going to be the right is going to be our h2 and the left will be our h1, right? Furthest away from the y-axis is your h2, closest to the x-axis, closest to the y-axis is your h1. All right, so now what we'll do is we'll now just define the double integral. Just remember that the g of xy is basically going to equal f of xy over the region that we're looking at, and then it's 0 everywhere else on the rectangular region. From a practical perspective, this is not going to make a huge difference. Right? This is more of a theoretical thing. So we're going to suppose that g of xy is the extension to the rectangular r of the function f of xy, defined on the regions D and R. That's that picture that we had earlier. Okay? The picture that we had earlier, just as a reminder, it's this one. That one right there. Okay? R is the rectangular region, D is the circular region, G is this piecewise function. Okay? Then g of xy is integrable, and we define the double integral for f of xy over d by the double integral over the region d f of xy dA equals the double integral of over the region R of g of xy dA. It's almost not, I mean, like, I don't know how much of a difference this is going to make to us working in multivariable calculus, maybe not a ton. But like, just get that this is the theoretical one. If at some point in time you do become a math major and you start looking at integration and things like the theoretical underpinnings of double integration, this will matter. Okay? So that's the first piece. The next piece that we're going to be looking at is Fubini's. Now we have something called the Fubini's theorem. It's called the strong form for Fubini's. We used Fubini's last time in order to actually allow us to, switch whether or not we were going to be integrating with respect to y first or integrating with respect to x first. We're going to do the same thing here. Okay? It's called strong form. What makes something a strong form is this idea that a weaker form is something that is only for a very specific or a more specific version of, say, in this case, the double integral. The strong form says, hey, look, we can now work inside of any kind of like form, or with any kind of, in this case, any kind of function. We don't have to stick to just rectangular regions or any kind of region. We don't need to stick to rectangular regions. And that's what makes it stronger. It's a stronger statement because it's more general. It works with more functions. Hence the phrase strong form. So when you're doing some math, that's why we use that term. For a function f of xy that is continuous on a region D of type 1, we have over the region D f of xy dA, okay? And basically what that says, okay, I can go from A to B, all right? And then g1 of x, g2 of x, f of x dy, and we saw that before. I showed you that before. So this is basically, I can integrate with respect to y, plug in the functions of x, right, and then integrate with respect to x. And that's for regions of type 1. On the other hand, I can also, for regions of type 2, what I can do is I can go in, I can integrate with respect to x, plug in my functions of y, and then integrate with respect to y and evaluate. And that, in fact, it ends up being the strong form. It's basically saying, hey, I can do it in either direction. I can either integrate with respect to y first, and then integrate with respect to x, or I can integrate with respect to x, and then integrate with respect to y. The two will end up being the same. And how we know that is notice, that's basically just saying, hey, that function, those two functions, they're exactly the same at the beginning there. What's key to remember is how do you set up the disk? How do you set up the region D? And how do you then set up your integral off of that? Okay? But that's what Fubini's allows us to do. It allows us to make a choice based upon what might actually be easier for us to work with. So let's do this. Let's evaluate the integral over a region D or a disk D of x squared e to the xy dA. And the region that we're going to be integrating over is this one. Okay? So we'll have the line y equals 1. Okay, first things first. So we'll make this 1, 2, 3, 4. Let's make that y equals 1. And we'll do y equals 1/2 x is the line that we're going to be integrating over, that we'll be integrating under. Okay, so that would be 1/2. So that's 1 up, 2 over. There we go. So this is going to be the area that we're going to actually integrate over. Okay? Now, what we'll notice, a couple things about this, is let's say, for example, I want to do it type 1. Okay? Type 1. So doing it type 1, the equation first is going to be y equals 1, right? Or, excuse me, g2 of x, the top one, is going to be y equals 1. So it's going to be g2 of x equals 1, right? Because that's the one furthest from the x-axis. And then our bottom one, our g1 of x, is going to equal 1/2 x. Okay, so that's that line here. It's y equals 1/2 x. And that's if we want to do a type 1. And then if we notice, we're going to go in here. We're going to say, okay, so the x value, this is going to be x equals 0. And then the other x value, imagine you've got a line that kind of runs down for this region. The other x value there is going to be x equals 2. That's the intersection of those 2 points, by the way. Okay, is x equals 2. So we're going to be going from 0 to 2. If we were to do a type 2, okay, we're now going to do a type 2. And what you want to look at is you want to say, okay, well, what are, I want to get my top function and my bottom function, okay? And actually, if you look here, we're going to just have the y-axis, okay, or excuse me, x equals 0 is the bottom, okay? So that's x equals 0. So the function that's closest to the y-axis is actually going to be g1, so our h1 of x, the one that's closest to the x-axis, h1 of x equals 0, and then our top function is actually just going to end up being, we take y equals 1/2 x, we get 2y equals x, so it's going to be h2 of x equals 2y. Or excuse me, these are both functions of y, pardon me. So h2 of y equals 2y, h1 of y equals 0. And then what we're going to do is we're actually going to figure out what are the values of y that we're going to be integrating with respect to. So we're going to start out with y equals 0. That's the bottom of this graph, right? That's going to be like right here. That's the y equals 0, and it's going to go up to y equals 1. So our y's are going to be between 0 and 1. And there we are. So it turns out, like in both cases, I don't know which one I would actually choose to use. Maybe I might, in fact, use type 2 because I think it might actually end up being easier. Okay, but we'll see. We're going to actually do both of them. We're going to do type 1 one, and we're going to do a type 2 one. So let's set up the type 1. Our type 1, we're going to set it up. It's going to be the integral. We're going to first put in our functions of y. Top one is 1/2 x, or excuse me, bottom one is 1/2 x. That's the bottom. Top one is 1. And then our bounds of integration are going to be from 0 to 2. And we'll do x squared e to the xy dy dx. Because we're going to integrate with respect to y first. Okay, these are functions of y, or functions of x. They are y equals. And then we'll do functions of x. So that's our type 1. Our type 2 then is going to go from 0 to 2y. And the bounds of integration goes from 0 to 1. And again, it'll be x squared e to the xy. That's our f of x. And again, dx dy. That whole g of xy thing that we had instead of the theoretical part of talking about talking about the double integral, like I said, from a practical perspective, I don't know how much of a difference it's going to make. We'll see. But for our purposes, you're just plugging in an f of xy, whatever the thing is that you're integrating over. Okay? And there is now our type 2. Okay? We've got a type 1, we got a type 2. Let's go in and actually do the type 1. We'll do both of them. So I got 1/2 x to 1, 0 to 2, x squared e to the xy dy dx. Okay? And so for our purposes, what we're going to do first is we're going to say, okay, I've got to integrate with respect to y first. So x becomes a constant. All right? X is a constant. And so this ends up equaling, and if x is a constant, then x squared is also a constant. So I'm just going to make the 0 to 2, and this will be then x squared, the integral from 1/2 to 1. Well, yeah, 1/2 to 1 e to the xy dy, and then we'll kind of do the whole thing dx. Okay? So this, remember, if we're taking the integral of e to some constant y, it's going to end up equaling 1 over c e to the cy. Okay, so just as a reminder that that's what's happening there. It just happens that x happens to be the value. So this is going to then equal, and this will be the integral from 0 to 2, okay, And then we'll have the x squared, and this is going to then be 1 over x e to the xy, evaluated from 1/2 x to 1. So this will then equal the integral from 0 to 2, x squared times 1 over x e to the x times 1 minus e to the x times 1/2 x. And so that's one of the differences there, is we're actually plugging in functions here. So this ends up being the integral from 0 to 2, x squared times 1 over x, and then this is e to the x minus 1/2 x squared. dx. Simplify that out a little bit. Really handy, should definitely do this. You got x squared divided by x, so that's going to give me x times e to the x minus e to the 1/2 x squared dx. And we'll be integrating that from 0 to 2. For our integration purposes, what we'll go in and do is we're going to say, okay, this is then the integral from 0 to 2 of x e to the x minus dx minus the integral from 0 to 2 x e to the 1/2 x squared dx. All right. So this thing right here, if we look at it, we're like, okay, cool. That's going to be an integration by parts. All right. So we'll let u equal x, du then is going to equal dx, and dv will equal e to the x, and v thus will equal e to the x dx. Or excuse me, e to the x dx, and v will equal e to the x. So we're going to get that this is going to equal the integral from 0 to 2, or, well, first, evaluated, we got x e to the x, evaluated from 0 to 2, minus the integral of e to the x dx, evaluated from 0 to 2, we'll get to there in a second, minus, and then this is a u substitution. So we'll let u equal x squared, du will then equal, or actually we'll let u equal 1/2 x squared, and we'll let du then equal x dx. So this is going to end up being the integral from, in this case, 0 to 2 of e to the u du, which would just equal e to the u, right? Evaluated from 0 to 2, which then would just be e to the 1/2 x squared, evaluated from 0 to 2. So just a little reminder about your integration there. So now this is just going to be e to the x. So this is going to be x e to the x evaluated from 0 to 2 minus e to the x evaluated from 0 to 2 minus e to the 1/2 x squared evaluated from 0 to 2. So this is going to be 2e squared minus 0 minus e squared minus 1, or actually in this case plus 1. Yep, minus e squared plus 1 because we got the negative, and then minus, just to keep my thing straight, this is going to be, we'll plug in 2 squared, that's going to be 4 divided by 2, so it's going to be minus e squared, okay, minus 1. So this is going to then be 2e squared minus 0. Okay, so we got the 2e squared, right? Minus an e squared, so that zeroes out. We're going to end up with a plus 1, so this whole thing equals 2. And that is your double integral, the value for your double integral over that region. So we went in, right, just like we had done in previous times. And we said, okay, well, what we'll do now is we'll go, all right, 0 to 2, 1/2 x to 1. We're going to be integrating with respect to y first. Notice we've got x's in that internal. That's what it should look like for this type 1. And then we integrate with respect to y first. Did that, okay? And then when we finished with that, we integrated with respect to x and then evaluated our bounds. Okay? Let's go in now and let's in fact do the type 2. Okay, so what I'd like to state right now is that in a different video, I actually went in, I tried to do it using type 2. I tried to do this particular integral using type 2. And I got through it and I discovered that it was just brutal. I mean, it was going to take me another 10 or 15 minutes, and I'd already been working about 10 minutes. And so, consequently, I was like, yay, this is a great example of a time in which doing it type 1 way actually is not that bad of an integration. Doing it type 2 way, terrible integration. So while we've set up type 2, I'm not actually going to torture you with doing it the type 2 way because it really does take a really long time. I'll do another one doing the type 2 way and show you, hey, this one actually is a lot easier to do type 2. Let's suppose that what we have here is we're going to say, all right, we want to evaluate this integral over a region D of 3x squared plus y squared dA. And let's draw what D looks like. And so D looks something like this, okay? D looks like this. It's going to be, we've got this curve, okay? And we've got this line, right? This line here is y equals x minus 3. And this curve is actually, it's two pieces. If we write it in terms of x's, it's going to be y equals the square root of x plus 3. And this one down here is going to be y equals negative square root of x plus 3. And so that'll be the bottom part of the curve. So we kind of have to break it up into two different curves. And if I think about this as a type 1 region, the type 1 region is actually going to have to be broken up into two pieces. On the one hand, we've got this piece right here, okay? So this piece, the front part here, we've got to have that integral, and that'll be then the top function will be y equals square root of x plus 3, and the bottom will be y equals negative square root of x plus 3. And then we'll have the second region, so we'll call that this region right in here. And then we'll have the second region, and the second region is going to be this region right in here, okay? And then that one will have y equals the square root of x plus 3 as the top, and the bottom will be then y equals x minus 3, okay? So we actually have to break this region up into two pieces, and that's more complicated, more work, more time intensive. We don't want to do that, okay? So instead, let's look at what happens if we think about it as a type 2 region, okay? As a type 2 region, what we end up getting here is I've got y equals the square root of x plus 3. And so that's y squared minus 3 is going to equal x. And then I have then y plus 3 is going to equal x, okay? And in that case, we see that we've got our, there's our, call that our H2, and here is our H1, okay? Because the furthest left curve is x equals y plus 3, and the furthest right curve is y squared minus 3 equals x. And they're both consistent. Consistently the furthest left, consistently the furthest right. Okay, so in this case, it makes much more sense to do a type 2. Okay, so that's then going to be that h1 of x, as we said before, is going to be, h1 of y, excuse me, is going to equal y squared minus 3, and h2 of y is going to equal y plus 3. Now all we need to do is find our bounds. Turns out our bounds in terms of y's now, okay, so we basically go in, we say, okay, so y will have y squared minus 3 equals y plus 3. So that gives me then y squared minus y minus 6 equals 0. So y equals, or y, yep, y squared minus, that means that we have y minus 3 times y plus 2 equals 0. So my bounds end up being y equals 3 and y equals -2. And those are the bounds then for my integration. So that actually allows me to just set up this integral pretty easily. I now am going to integrate, I'm going to go from -2 to 3, and then remember my bottom curve is going to be y squared minus 3 up to y plus 3. And then my function, my g of xy, or f of xy, either way you want to look at it, is 3x squared plus y squared. So it's going to be 3x squared plus y squared. We'll integrate, since there are y's here, we're going to integrate with respect to x first, and then we'll integrate with respect to y second. And there we go. And that's our setup. So now what I'm going to do is I'm going to say, okay, first I'm going to integrate with respect to x. Y squared is constant. So this then gives me 3 over 3x cubed plus y squared x, evaluated from y squared minus 3 to y plus 3. So let's just do this first, so then I'll plug it into my integral. So this ends up being y plus 3 cubed plus y squared times y plus 3 minus, and this will then be y squared minus 3 cubed plus y squared times y squared minus 3. We'll go in, we'll evaluate that. Just give me a moment. So when I go through and I evaluate that is, that I get y cubed plus 9y squared plus 27y plus 27 plus y cubed plus 3y squared minus y to the 6th minus 9y to the 4th plus 27y squared minus 27 plus y to the 4th minus 3y squared. All right? So, you know, big ass polynomial. That's fine. And so now what we're going to do, let's go through and let's simplify this out. Simplifying there, we get negative y to the 6th plus 8y to the 4th plus 2y cubed minus 12y squared plus 27y, and then well, actually this is going to end up giving me plus 54. Always good to check your work. Plus 54. Okay? So now that's going to be the thing that we have inside of our bounds of integration. So now I have from -2 to 3 of negative y squared, negative y to the 6th plus 8y to the 4th plus 2y cubed minus 12y squared plus 27y plus 54. And you may be thinking to yourself, my God, double integrals take a lot of calculation and a lot of integration. That's true, they do. What are you going to do? That's it. Okay? So now we just got to integrate with respect to y. Well, that's not so bad. So that's going to be negative 1/7 y to the 7th plus 8/5 y to the 5th plus 2/4 y to the 4th minus 12/3 y cubed plus 27 over 2 y squared plus 54y, all evaluated from -2 to 3. Okay, so now we're just evaluating this all from -2 to 3. When we do that, okay, I would just plug that all into my calculator, and this ends up giving me now 2,375 over 7. All right? I know a lot of algebra going on in there. Not too bad, though. Nothing too tricky. Just a lot of simplification. So make sure you do go in there and you do the simplification as you work. And then once you get up to here, I mean, just plug that into your calculator. And that's what I would do. Okay? Key point, though. Notice that in this case, it's so much easier for us to use type 2 versus doing a type 1 where we'd actually have to do that stuff twice. What you really start to notice as we continue to work here is that cutting down on the calculation is going to make a huge difference for you as you do multivariable calculus.